Let me begin by thanking the organizers for this kind invitation. It is a kind invitation because I have to begin with a confession, and that is I don't work on automorphic forms. So I'm an imposter to this group, not a card-carrying AFART member, as it were. But by the end of the talk, I want to try to convince you that I'm not that far either. I'm kind of a benign, distant relative, second cousin twice removed. And I work on a subject called homogeneous dynamics. So this is the study of dynamical systems on spaces that you've been seeing all week, which are spaces like SL2R factor SL2Z, or an adelic quotient like SLN of the adels by SLN of Q, which came up yesterday, and things like this. So I do a kind of complicated mathematics where you take some point on this space and you move it around according to some rule. And magically, this seems to correspond to, this sheds light on questions in number theory, specifically, the age-old subject of Diophantine approximation. This sounds kind of bizarre because why would moving things around on a quotient of a Lie group by a discrete subgroup have anything to say about numbers? And the bridge that unites these two is something that is given to us as a gift by the automorphic forms community. So my job today is to try to explain all of this in the next hour using an example, which is a recently concluded paper joined with two very talented young mathematicians. Gaurav Agarwal is a postdoc in Zurich. Saurav Das is a postdoc at the Tata Institute. And this is the title, but the story is much simpler than the title would suggest it is. So please bear with me. Awesome. Excellent. Okay. So let me begin by showcasing the application that we have in mind. This is an application to Diophantine approximation. So as we all know, human beings are hardwired to understand integers and rational numbers. But the sad truth is that most numbers we encounter are neither integer nor rational. So how does one progress? How does one proceed? One proceeds by trying to approximate these irrational numbers as best we can using the objects that we know, which are integers and rational numbers. So for the basic question in Diophantine approximation is, if you take an irrational number theta, how small can you make the difference between theta and a rational number p over q with good control over p and q, okay? Of course, we know that the rationals are dense, so you can get very close, but you now want to kind of scale up this thing and have good control over the rationals. And this question is the same as the question of considering the distribution of the sequence q theta mod 1 near 0. Okay, and this is a very interesting question with lots of nuance built in. A similar question, which I think is very natural, is rather than considering the distribution of q theta mod 1 near 0, you might as well consider its distribution near another number, right? So instead of looking at q theta minus p, this amounts to studying expressions of the type q theta minus p minus c. All right, so there's a shift to the problem. This shift causes the problem to be called inhomogeneous. That's the inhomogeneous in the title. You can forget about the word as such. It just means that rather than considering theta minus p over q, I'm considering q theta minus p and adding a shift to it. I want this quantity to be small, all right? I think it's a natural problem to consider, and indeed, it's something that comes up a lot. So this kind of approximation where you have a shift occurs naturally, so to speak. So if you look at, for example, quantum mechanics like the Berry-Tabor conjecture and so on, eigenfunctions and eigenvalues of the Laplacian on flat tori, this kind of, the distribution of this kind of object occurs quite naturally in these questions. Okay, so let me scale up this problem. Rather than looking at one integer, one real number theta and a shift, I'm going to take a pair, theta comma c. This is my general setting. The number theta is replaced by an m cross n matrix theta, and the shift is replaced by a column vector, an m cross 1 vector, c. And this pair gives rise to a system of affine forms. There are m affine forms. And now I want to ask the scaled up question, how well does theta q mod 1 approximate c? Equivalently, can I efficiently find a pair of integer vectors p comma q which simultaneously make all these linear forms small in value? Okay, this is my basic question. It's a question which has been studied extensively over the years. So the setting is clear. I started off with a real number theta, tried to approximate it around 0, and then added a shift. Now I'm just scaling everything up, replacing theta with a matrix. So Q is a vector in Zn. This is an m cross n matrix. So I'm multiplying the m cross n matrix with an n cross 1 matrix and adding an n cross 1 shift. Okay? That's what it is. And I want to make the entry of these linear forms simultaneously small. There is a slightly finer question which I'll dwell on towards the end, so I just might as well introduce it now, which is that sometimes it's interesting and worthwhile to allow the different linear forms to have different rates of approximation. This amounts to putting a small weight on the denominator q. If it's too much now, don't worry about it. But this is, rather than looking at forms which are simultaneously becoming small at the same rate, I'm just adding a small number here in the power, which causes different rates of approximation in different directions. This is, having baked a cake, this is trying to put some icing on it. Don't worry if it doesn't appeal to you. So with this, I'm ready to state the first major result of the day, which is due to Wolfgang Schmidt. And for that, I'm going to introduce a counting function. So my one-line description in my CV is that I'm a person who counts using ergodic theory. And that's what I'm going to try to explain today. How does one count using ergodic theory? This is a counting function. It counts the number of solutions to the previous inequality, this one, where the number of the height of the solution, the heights came up yesterday, is some notion of height of a solution, a proper function, is bounded. Okay, so there are finitely many solutions in some regime. I want to count them and get an asymptotic formula if possible, or whatever I can get. If I get an exact formula, that's even better. But I want an asymptotic at the very least. And Schmidt has a beautiful result. So this says that regardless of what the shift is, for Lebesgue, almost every matrix in the cube 0, 1 in M, in the space of matrices, this counting function has an asymptotic formula where the main term is log t, and the error is the square root of log t. Okay? It's a beautiful result. It tells you, it's, if you've not encountered this kind of work before, cast your mind back to the Gauss circle problem. Okay? This involves taking a circle in R2, centered at the origin, and asking yourself, how many lattice points? All right? And we still don't know the exact shape. Of course, we know the main term. The main term is the area of the circle. And conjecturally, the error is the square root of the main term. All right? That's the Gauss circle problem, still open. This is a variant of this Gauss circle problem where you have a different shape, not a circle. You have some kind of shape, and you're intersecting that shape with a ball and asking for lattice points in this area. And what Schmidt is saying is, like the Gauss circle problem, the lattice points in this area also correspond to the volume of the area, which is log t, plus the square root of error. So it's kind of a really good situation. It's a Gauss circle problem where you're getting the right error, right? And the constant is exactly given by this, it's a certain volume. So the next step after someone's counted this for a probabilist, this looks like a law of large numbers. And so the next step would be to try to understand the fluctuations around the mean of this counting function. In other words, is it possible to get a central limit theorem? Okay? Yes. Yeah, so these inequalities define some region. It's an infinite volume region, and you're counting integer points in this region. So let's say you take, it's, in like the case of one linear form, it's some kind of a line or a plane, and you're trying to count, integer points close to this line. And you box them up or put them in a shell and then ask how many there are. So it turns out that the solutions to these inequalities, which are these lattice points, distribute themselves quite evenly. And so they're kind of equidistributed in this space. And so they asymptotically tend to the volume of this strip. That's what the meaning of it. Okay, so central limit theorem. So this has been considered by a lot of people. Let me give you a little bit of background and prior work. A lot of work was done in the last century, beginning after Schmidt proved his law of large numbers. So Walter Philipp and Simmer and several other people used powerful techniques from one dimension. So in one dimension, you have the very powerful continued fraction expansion of a number. This continued fraction expansion has a property which was gifted to us by Gauss, which is that it comes associated with a dynamical system called the Gauss map. So Gauss, one fine day when he was very young, plucked out a ergodic invariant measure which kind of talks to the continued fraction expansion. And this is a very powerful tool which allows you to, quote unquote, symbolically realize the continued fraction expansion of a number. And symbolic dynamics is a very powerful subject which is then put to good use to prove one-dimensional CLTs. So then the story fast forwards to about 10 years ago, when two sets of people, the first was Dolgopiat, Fayad, and Vinogradov, and the second team was Brocklund and Gorodnik, used very modern techniques to prove a higher dimensional analog. And these modern techniques use spectral methods from automorphic forms. I'll come to that in more detail when I describe our result. And these kind of propelled the question of counting these results or getting CLTs or more refined information into, put them into a modern setting. A few years ago, Gaurav and I proved a slightly more complicated central limit theorem. But the main interest in this is it uses something involving Eisenstein series. I'll come to this later on. Okay, so the summary that I want to present to you is a lot of work was done in the last century. These are two representative works of that period, but there's a lot of work. And then in this century, we have kind of upgraded everything to higher dimension using homogeneous dynamics, using the spectral theory of automorphic forms. All right. And so in conclusion, all previous results are either don't admit a shift or admit a fixed rational shift, which is Gaurav and me, or they allow you to vary both the shift and the variable, okay? So today I'm going to try to tell you about a result. Let me just go back to the inequality. I'm going to tell you about a result where, so, here there are two variables, there's theta and there's xi, okay? And a probabilistic result, you have to kind of set your stage. What are you going to allow to vary? Okay, you could allow theta and xi to vary. That was what was done in Dolgopyat, Fayed, Vinogradov and all. But you could also try to fix one of these guys. And that's a more nuanced problem. Averaging over a smaller family of parameters is always harder than averaging over a fuller family. So today's our whole talk today is based on fixing the shift. You fix the shift and try to do some analysis. Okay, so that's the thing. And what shift am I going to fix? I'm going to fix a shift which admits very, very good approximations by rationals. So these are the Liouville numbers, okay? I'm going to fix a shift that is a Liouville number, or more generally a Liouville vector. A vector is called, let me recall that a vector is Liouville if for every positive E, there exists infinitely many integers, vectors P comma Q, which which solve this inequality. So it admits excellent rational approximations. Because it admits excellent rational approximations, there can't be too many of them. So in fact, they're uncountable, but have zero Hausdorff dimension. It's a really kind of small in some sense. Okay? And here's the famous example we've all learned when, at some point when we were children. So here's the first result of today. And let's walk through it slowly. So remember that, so the setup is, I'm going to consider those inequalities that we saw, but I'm going to fix the C, which is a non-Liouville number vector. Okay, so this is the complement of the zero Hausdorff dimension set. Then I'm going to take the counting function that Wolfgang Schmidt studied. He proved that asymptotically, it's actually roughly this constant times log t, right? So I'm going to subtract the main term, normalize, and try to see, how this deviates from the mean. So I'm going to look at the set of matrices for which, when this difference from the mean, normalized difference from the mean, is less than eta, I'm going to try to see what happens to it. And the answer is that this actually converges in distribution to the Gaussian. Okay? So there's a central limit theorem with an explicit variance for Schmidt's result. So it's an upgrading of Schmidt's result. It says that not only do you have the law of large numbers, you also have convergence to a Gaussian, right? Okay? That's the result. I called it the first theorem because I'm going to recast this in terms of weak convergence of measures, which we saw yesterday. I was very happy that we saw weak convergence of measures. This is going to be recast as a theorem on the space of lattices about weak convergence. All right, this is the theorem. And the one-line takeaway is the normalized fluctuations of the counting function around its mean converge in distribution to a Gaussian, provided the shift is a fixed non-Liouville shift. So I should add that if you allow the shift to vary as well, then this is a theorem which is difficult to prove, but easier than this. Okay, the complication, as it were, is in fixing an explicit shift. All right, that's the thing. Okay. So some commentary on the results. So even if I don't have that, in the second slide, I told you I'm going to change the rate of approximation. Even if we do that, but even if I don't, it still sheds more light on Dolgopyat, Fayed, and Vinogradov, because we explain to you which shift you can fix. But this leads us to this question over here, which is that Wolfgang Schmidt's result was true for any fixed shift. He did not have to assume it was Liouville or not Liouville or anything at all. He could fix whatever shift he wanted and get an asymptotic count. Is it possible to get a CLT for any count? And the situation is kind of strange. On the one hand, this result that I'm describing today is proved for vectors which are not Liouville, so kind of irrational. But previously, Gaurav and I already proved it for rational shifts. So in the other direction, we used over there a fact that if you want to study a rational shift, it amounts to doing analysis not on SLNR factor SLNZ, but on a congruence quotient. And one can still build the tools necessary on this congruence quotient and proceed. So we are in a kind of situation where we know the rational and the irrational, but the middle ground is still not understood. I would say that it should be true for any shift. Okay, so far so good. Are there any questions before I move on to the next section? Yes. Yeah, so I'll explain it. Basically, what happens is I have to stay away from the cusp, but I also have to simultaneously stay away from some rational sub-varieties. And so if I'm Liouville, then I tend to drift very close to these guys. And I get caught. That'll come up. Okay, so now I'm going to move from this number theory result to a result which is closer to the topic of this conference, which is we are going to do some analysis on the modular surface and relatives. And the connecting bit is this object called the Siegel transform. Okay, what is this? So the reason that one can get results in Diophant approximation using this kind of technology is that the space SLNR factor SLNZ, which we know because we are in this workshop, it's SLNR is a nice a Lie group, and SLNZ is a discrete subgroup where this quotient, even if it's not compact, it's the next best thing. It's a finite volume quotient, right? So you can normalize to get a probability measure on the quotient. In other words, the Haar measure on SLNR descends to a probability measure on this, and we all seen the fundamental domain in the modular surface. This space admits an identification with the space, with the moduli space of co-volume 1 lattices in Rn. Okay? So it's easy to see. What's one co-volume 1 lattice in Rn? Zn. Yes? Fundamental domain is square. And every other such lattice is obtained by an action of a matrix in GLNR. But if I insist on the volume of the fundamental domain to remain 1, then I have to act, no choice but to act with the determinant 1 matrix because the volume scales with the determinant. Okay? So this gives you an action of SLNR on the space of covolume 1 lattices. It's a transitive action, and the stabilizer of SLNZ of Zn is SLNZ. So this is a very important identification. And now we come to this very important object called the Siegel transform. So Siegel transform is defined as follows. You take a bounded, compactly supported function on Rn and define the Siegel transform of a lattice. The Siegel transform is a function on the space SLNR factor SLNZ to just be the sum, you take all the vectors in the lattice, all non-zero vectors, plug it into this function. It's a sum. It's very kind of reminiscent of an Eisenstein series, right? And this thing has transformed a lot of mathematics over the last, I would say, half century, because this is the tool connecting number theory to homogeneous dynamics. It's also the tool connecting counting problems in the subject of flat surfaces. So for example, Eskin-Mirzakhani and things like that. Moduli space of flat surfaces, Teichmuller theory. There's an analog of the Siegel transform, and that is a very fundamental object which allows you to count objects in that moduli space. So what we're interested in doing is, let me tell you why this comes up. Siegel proved a beautiful mean value formula around the 1940s or 50s, and it says the following. It says that if you take the Siegel transform of lattices and average over the space of lattices, so the space of lattices, as we have just seen, admits a probability measure. So integrate your function over the space. Then what comes out is the integral of the function that you fed into the Siegel transform over Rn. Okay? If you instead define your Siegel transform to only sum over primitive vectors, then you get a factor of 1 over zeta n. All right? Okay, great. So what does this have to do with counting? But now it's looking a little more promising. What you can do before I go to counting is what we need later on is not just the Siegel transform, but also higher moments of the Siegel transform. So there was a mathematician called Rogers, C.A. Rogers, British mathematician, who wrote a beautiful paper. I think the paper deserves to be better known than it is. But he computed the higher moments of the Siegel transforms, which means that you square the Siegel transform and average it. You cube the Siegel transform and average it. And you could imagine that this would be a kind of impossible thing to handle. But in some, at least in lower, the lower moments are tractable. So here's the second moment, for example. And there's something for the third moment. And this should kind of ring a bell for you, because whenever you're trying to say count something or prove a central limit theorem, the higher moments are going to come into play. Okay? Higher order correlations are going to come into play. So let me give you a beautiful application of Siegel's formula due to Wolfgang Schmidt again. The fact of the matter is that if you feed the indicator function of a set into the Siegel transform, then the Siegel transform is simply the number of lattice points in that set. That's what it is. And Siegel's theorem tells you that the average lattice has the expected count, which is the volume of the ball. Okay? But you can do much better. So here's some nice work due to Wolfgang Schmidt. You can try to do the same thing that we are doing with those inequalities. You can say, well, okay, how far off from the expected value is the number of lattice points? So you define the discrepancy of a lattice with respect to your set to exactly be that difference divided out by the volume. Okay? Feeding this discrepancy into feeding the indicator function and getting the second moment estimate will straight off give you a mean square discrepancy upper bound. Right? It's just feed it in and this pops up. Okay? So this provides a link between counting problems involving lattices and the space of lattices. So here's what Schmidt proved. He proved, in fact, that you can get a very sharp bound. You can get, for almost every lattice, there is a constant. As the discrepancy has a pointwise bound of log square of the volume divided by the square root of the volume. And there are some remarks about the discrepancy and so on. But what I want to emphasize in this part of the talk is that this Siegel transform is kind of a very fundamental object. One thing which is of great interest to people, I think in both communities, automorphic forms as well as dynamics, is that it's not, it's kind of natural to try to set this up for other homogeneous spaces, like, the quotient of the symplectic matrices by integer symplectic matrices and so on. And indeed, Andre Weil proved a version of Siegel's mean value formula for an arbitrary semisimple group. What is not known, however, is the second moment formula or higher moment formulas for, say, take a semisimple Lie group, any semisimple Lie group which, admits the Borel-Harish-Chandra formula, take the integer points, set up the Siegel transform, and compute the higher moment. So this is kind of a situation where the high-powered machinery of Eisenstein series enters. And this picture is far from resolved. If someone resolves, every single instance of someone proving a higher moment formula for these objects leads to a wealth of applications. All right. Okay, so the space that we are going to work on today is not the space of lattices SLNR factor SL and Z. It's a related space. Remember that we had a matrix and a shift. So I have to find some way of encoding the shift. And I'm going to encode it using the space of affine unimodular lattices. This is, I'm defining on the next slide, but it's a semi-direct product of SLNR with Rn, factored by a semi-direct product of SL and Z with Zn. And this admits a particularly easy looking Siegel transform in the first moment and the second moment. All right. So paradoxically, somehow once you know the Siegel transform and second moment formula for SL and R factor SL and Z, getting it for a torus bundle over SL and R factor SL and Z is not that difficult. So let me now move to dynamics. I'm doing fairly well on time. And this is the space that I'm going to work on. The group is going to be SLDR semi-direct RD. The lattice is going to be SLDZ semi-direct ZD. So this is just a torus bundle over SLDR factor SLDZ. This also is a lattice in the gamma tilde is also a lattice in G tilde. And I'm going to single out two kinds of subgroups of SLDR. One is a subgroup of diagonal matrices, such as these. If you don't like these weights, which are put here to deal with those complications of weights that we discussed earlier, you can just manufacture it so that everything adds up to determinant 1. This is a diagonal group, and this is a unipotent group, subgroup of SLDR, where I take I take an M cross N matrix theta. So M plus N should add up to D, and plonk it in the upper right column. Okay? So let me take a step back and go back to the modular surface, right? If I go back to the modular surface, then I have my quotient is SL to R factor SL to Z. And I have two subgroups. One is the diagonal subgroup e to the t to the minus t. I'm calling it, let's say, AT. And the other is the subgroup I call U theta, which is 1 theta 0 1. All right. So in this space, these two have geometric meaning because we know that SL to R factor SL to Z can be viewed as the unit tangent bundle of the modular surface. All right. And the modular surface admits two distinctive flows. The first is obtained by going at unit speed along a geodesic, called the geodesic flow. And the second is obtained by going at unit speed around a horocycle, which is a circle tangent to the x-axis. It's called the horocycle flow. The nice thing about these two flows and the area of homogeneous dynamics as such is that they admit an algebraic description. So the horocycle flow and the geodesic flow can be represented by the left action by multiplication of these two guys on this homogeneous space. Okay? This is the geodesic flow, left multiplication by a diagonal matrix, and this is the horocycle flow, left multiplication by an upper triangular matrix. That brings us to the end of the similarities between these two guys, because they're really very, very different, right? The geodesic flow is, both flows are ergodic and mixing and so on, but this is exponentially mixing. It's very chaotic. The horocycle flow, on the other hand, admits a structured kind of chaos. So it admits a beautiful set of, it admits a beautiful rigidity, which is unlike anything that people in dynamical systems are used to. These nowadays go by the name of Ratner's theorem. Which are resolution to very famous conjectures of Dani and Raghunathan. And what it means for is that this, and it's kind of, let me draw an artist perspective of the space SL to R factor SL to Z. I'm drawing it as a balloon with a cusp. Okay? Finite volume, non-compact. And so the version of Ratner's theorem in this case, which is due to Fürstenberg and Dani, depending on the context, says that no matter which point you pick, if you start flowing by this upper triangular matrix, there is a complete description of every single orbit closure. Every orbit is either dense or periodic. And every ergodic invariant measure for this, remember yesterday we learned that the space of measures is infinite dimensional. All right? So imagine how startling it is that it's possible to describe every single ergodic invariant measure for this flow. They're either supported on a periodic orbit or they are the Haar measure. There are only two possibilities. Okay? Very rigid situation. And this then scales up to arbitrary semisimple Lie groups and actions of subgroups generated by unipotent. They don't have to even be unipotent. You could act by SL to R, which is not unipotent, but is generated by unipotence, and the same rigidity is true. All right, so let me skip this for now, I'll come back to it. So this is a theorem of Nimish-Shah, which is the qualitative theorem that underpins our technology. We have to improve it in two different levels. But Nimish's theorem is a version of Ratner's theorem for the semi-direct product that I just put up. Okay? The space is SLDR semi-direct RD, factor SLDZ semi-direct ZD. And Nimish says he wants to describe the orbit closures and ergodic invariant measures for this translates, for geodesic translates of this upper triangular group. And it turns out that going to the cusp is not the only obstacle. There is a family of rational shift subvarieties. Okay, so it's a description which I'm not writing out, but think of it as an accountable family of rational subspaces in this space, such that if you start off on one of these spaces, you're going to get trapped in it. It's like a version of a periodic orbit. Okay? You're not going to come out, so you're going to accumulate on this space. And so what Nimish proved is that if you don't start off on this space, then in fact, the orbit measure that you have weakly converges to R. Okay? So here we had a situation where you could have been stuck on a periodic orbit, and that's it. Or you equidistribute everywhere. In this torus bundle situation, you have this space as the base and a bunch of tori at each point. There's a torus at each point. There is a countable family of subspaces where you are still likely to get stuck. If you don't start off in these countable family of subspaces, you're going to equidistribute in the whole space. That's his theorem. And this theorem makes essential use of Ratner's theorem and also something called Dani-Margulis linearization. Okay? So the first thing that we will do is we want to get some quantitative version of this. And this is a beautiful theorem proved by Woo-Yeon Kim, young Korean mathematician. And Woo-Yeon says, okay, I want to start off not trapped on the rational subspace. And I'm going to quantify that using a certain function zeta. So I'm going to say that let me start with a coset in the space of affine lattices comprising a matrix G in SLDR and G times V is a vector in RD. So this is a coset in this space of affine lattices. And I'm going to impose a condition on this matrix. This condition guarantees that I will not be on the countable family of rational obstacles to begin with. So once these two conditions are satisfied, I'm going to equidistribute to Haar. Not only am I going to equidistribute to Haar, I will do that at an explicit rate. Okay, so this is kind of a very major theme in homogeneous dynamics these days, which is having understood Ratner's beautiful theorems and the work of Dani-Margulis and others, all of it, I don't know, have you guys ever seen the Birkhoff ergodic theorem? No? Okay. Let me tell you what it is, because otherwise you won't appreciate this result. Right? So ergodic theory is the study of chaotic objects. It was initiated by the Austrian physicist Boltzmann and people around him. And it came out of the realization that microscopic particles which are moving chaotically are not subject to Newton's laws as such. So what Boltzmann's insight was is it's profitable to try to study long-term averages of these things. You know, you can't solve one of those problems about train A leaving station A and train B leaving station B. When do they meet? With gas molecules. They're not going to, that doesn't work. So instead of trying to predict what's happening in 2 minutes time, I'm going to average out. I try to predict what happens in say 100 years or 1,000 years, okay? So the prediction that Boltzmann had, his ergodic hypothesis was that over long ranges of time, if you have a chaotic particle like oxygen molecules in this closed room, they're going to spread themselves out evenly. Okay? And what it means is if you do a time average, over a very long period of time, it's constant. And the constant it is the volume of the space where the motion is going on. This is that time average. Okay? And this is the space average. There's no t dependence here. All right? This was rigorously proven by different levels, different types of functions by von Neumann and Birkhoff and so on. But all these have the property that they don't admit a rate. So you can't stop the flow and say, okay, how much have I covered? You can't ask for a finitary version. This is because of a fact involving abelian harmonic analysis. All right? If your action, the group action which is R or Z over here, if it was an action by a semisimple group, then the representation theory of semisimple groups would kick in and you would be able to give an effective average. Right? But for abelian groups, that is not the case. And nowadays in our community, one of the main challenges is, can you force these Ratner's theorems should be viewed as a very, very sophisticated Birkhoff-ergodic theorem. And the challenge is, can you get a finitary version of Ratner's theorems? This is one such. Unfortunately, this is not good enough for us. So what we had to do was prove a version of this which is called multiple equidistribution. So equidistribution not just at one scale, but at multiple scales. Okay? The theorem itself is kind of a mouthful to talk about. So I'll not talk about it on the, in a few slides. I have a version with two functions. I'll tell you what I want to do there. Okay, so let me see. Yeah, let me go to the proof, and then the proof has a two-factor thing. So I want to, let me go back, take a step back. I want to prove a central limit theorem. The central limit theorem uses higher order correlations between observables. Okay, so I need to factor in how these observables interact with each other. In order to do that, I need to get not just an equidistribution, but a higher order equidistribution. There's a standard way of doing that, and that is using induction, right? So this is well known. What it involves is two facts. The base fact, which is how do you get equidistribution in the first place? The machine, at the very bottom of this all is a fact from the representation theory of semisimple groups. It is that the regular representation of the group on the group factorial lattice on L2 of G mod gamma admits a spectral gap. The extent of the spectral gap is governed by more sophisticated conjectures like the Ramanujan conjectures. But the existence of the spectral gap is enough for people like me to start the process of getting some deviation on average in these correlations. So the base case for us is Kim's theorem. Kim's theorem, which was this quantitative version of Nimish-Shah's theorem. And what I need to, basically, once I convince you that I can go from this base step of Kim's theorem to double equidistribution, I'll be done. So what do I need to do for that? I need to try to look at, on a small scale, I need to look at the measures supported on a small piece of this translate as theta varies in my unipotent. All right, so there's some density which dictates how theta varies. And I want to show that this is not too far from the heart. This measure is not too far from the heart with a certain specific form of error, tightly controlled error. This is what I want to show. Once I'm able to show this, I know how to pass using arguments which are now standard. And so here's the term that, here's the kind of thing that I want. I want a product of functions. I want to control a product of functions of this kind. And so what I do is I perform a dyadic decomposition or similar decomposition of the interval and write out my parameter theta in terms of this density. To get and expand out, I get some sum like this, of which one term is essentially a constant. And so I want to focus my attention on a term of this kind, using some standard tricks from Lie theory, which is, conjugate and conjugate back and absorb some stuff. You come down to focus on terms like this. And to this, I want to apply single equidistribution because I magically moved from two functions to one. The issue here is that the rate of convergence depends on this base point, which I have shifted. All right. This problem is quite a problem because what I have now is a situation where I have to control my orbit going into the cusp. I also have to control the countably many SL2R invariant embedded subspaces, which I have to avoid. Both of these together. And here, we are able to show that Kim had this zeta function, which he used to quantify being away from these subspaces. So what we're able to do is show that violating Kim's condition is equivalent to having a short vector in a thin cylinder for a certain lattice. Okay? This is what we're able to show. If you do end up in one of these SL2R invariant rational subspaces, that means that this particular lattice, where G and GV are the parameters that are the coordinates for your lattice, this particular lattice has a short vector in a cylinder. Okay? And we are able to show that this almost never happens. How to do that is a very interesting story. So this is around 15 years ago, there was a kind of breakthrough in homogeneous dynamics, which was the classification of stationary measures for random walks by Benoit and Kant, which played an instrumental role in Eskin-Mirzakhani. We use something called the height function machinery of Benoit and Kant, which was developed further by Ronggang-Shi, to show that this almost never happens. So as long as your shift is not Liouville, this particular thing is not going to happen. Once this doesn't happen, you can exercise enough control over the changed base point to make sure that you equidistribute properly. That brings us to like part one of the proof. Part two of the proof is to put all this into a standard toolbox you borrow from the probabilists. You can choose one method of proving CLTs. We chose a method of moments. And then you have to feed all of these into the moments and do some further, analysis, some of which is not very easy, some of it is not bad. But that's a different story. I think I've, spoken enough today. I'll stop here.
Any questions or comments?
Yes. Yeah, so that comes up it naturally comes up in the cumulant calculation. Yeah, so there you can really see why they. Yes, sigma squared. Yes, exactly.
Can I ask a naive question?
Yes.
So from SLNR mod SLNZ, then from SLN you went to this SLN symmetric product
Yes.
Rn.
Yes.
I was just wondering, is it of any use to consider pick some representation of SLN?
Yes.
Call the representation space V and look at SLN symmetric product V.
Yeah, absolutely. Absolutely.
So people look at this?
Absolutely. So in fact, a lot of people have looked at it. Very, very relevant is a paper of Andreas Strombergson, where he does exactly this. He looks at SL2R, a representative SL2R, and then gets effective versions of Ratner's theorem on that space. That's actually something which, is a natural next step, definitely.
Can you go back to your main, the theorem is the statement?
This one or the other one?
No, the previous one.
Yeah.
Now, and you made a comment about this Gauss circle problem.
Yes.
So suppose you're counting the Gauss circle problem and minus the leading term divided by the square root of the leading term.
Yeah.
Less than eta, and you count.
Yes. Yeah, you get this.
You get something.
Yeah, you get something. So there's this guy. You get lots of very cool stuff, and there's this guy at Rutgers called let's say Beck.
Mm-hmm.
Who has very sophisticated, versions of the Gauss circle problem. But of course, you won't get the right error because you don't even have it. You'll not get the square root error. But yes, you have a lot of. See, for us, the thing is that we are using, without stating explicitly, a lot of symmetry in the problem, which is helpful for us. For instance, when we want to use spectral information, it helps to have functions which are like k finite or k invariant and things like that. And in this kind of situation, that directly translates to some kind of constraint on the counting problem. Because ultimately what we're doing is taking the indicator function of the counting problem, passing it through some complicated machine, and bringing it out on the space of lattices, and then doing something and pushing it back. But so the geometry of the problem is a big constraint. It really has to be something which is tractable. If you change it a little bit, then everything falls apart in